Today I'm going to show you my attempt at recreating Minecraft in 1 week. This project will be on GitHub, so if you think a week's worth of work is worth a second of your time but hours worth of information, click the big red subscribe button and smash the like icon, and let's ponder the question,
what if?
No. How do we create this simple Minecraft? Since the last video, I have added terrain, biomes, a 32 block texture atlas, biome specific objects like cacti and pumpkins, biome specific trees, mining and a work in progress TNT explosion, water and player buoyancy, dynamic chunk loading and unloading, flowers and grass, underwater seagrass and kelp columns, dynamic post-processing, and a simple inventory. Yep, so that's what we're going to try to get through today. So let's begin with the concepts. We all know that we can create 3D voxel chunks using 3D noise, but the problem is that it's not really like real terrain at all. We can fix this by using 2D noise function and subtracting the Y position from that function. Then, if the value is above a certain threshold, we set the voxel to be a grass voxel, otherwise we set it to be an air voxel. We can also use 3D noise to add variability to the terrain. Here I have layered multiple octaves of 2D and 3D simplex noise. The Unity to Mathematics library comes with very fast noise functions. The chunk dimensions I went with were 16 by 90 by 16, represented by the Unity XYZ coordinate system. The voxel array stores ints instead of bools for solid and empty voxels. Different ints, which I call block indices, refer to different block types. This is how I created the cool terrain shown here. If this was confusing, I would recommend you check out my previous tutorial on voxels, which goes in depth into the algorithm. To turn this into an infinite terrain, I made another script which would instantiate and destroy game objects dynamically around the player. To do this, I simply create a dictionary that would store the chunks and a vector2int key for them. The vector2int represents the ID of the chunk. This line of code is used to calculate the player's current chunk ID. Then we loop through the chunks and instantiate game objects, and we add the game object and the chunk ID to the dictionary, so that when we spawn new chunks next time, we do not spawn chunks that are already there. This GitHub page has a script, so check that out if you want some more information on how it works, and everything is commented for the ease of reading. Back to the chunking system, inside the update loop, we check through the whole chunks dictionary. If a key is too far away from the player, then we disable it and remove the key entry from the dictionary. Texturing is also quite a simple concept. We need to create a function to which we can provide a block ID, and it would add the correct UV coordinates to the mesh. In the previous tutorial, we did this by hard coding it into the faces, but as we need to create a lot of different block types, we cannot do this. Instead, each face contains one index which tells us which orientation it is in. The top is 0, the side is 1, and the bottom is 2. To convert the single block index into a vector2, we use this bit of math. If we say pass 3 into the function, and the texture is of size 8 by 8, it'll return 3 and 0. If we pass in 30, it'll return 6 and 3, etc. We divide this by vector2 by 8 to get the position in texture coordinates between 0 and 1. We can now define the other corners of the sample positions from the texture. To do this, I calculate a step, or the width of each block face of the texture. Then I add to the main vector2 a series of vector2s that defines the 4 corners of the texture. Then I add these 4 vectors to the UV list, which allows us to texture the terrain like so. The way biomes are created in many games is by creating 2 height maps from vastly different sample positions. We can define both height maps as a temperature and a rainfall map. Now you can see I have made a couple of if statements which check what block type the block is. I also used elevation to decide where the snow is going to go. And that's basically how the biomes were created. Very simple. Mining in a voxel game is done by editing the voxel array at the position where we click on the fur chunk. As you can see here, we have made a script where when you click, a raycast is shot from the position of the camera. If the right mouse button is pressed, we add a block, and on the left mouse click, we remove one. To find the location of the click, we first need to get the position of the click in world space. Then we subtract the raycast position from the chunk position to find the local click position. Then, to find the block that we want to edit, we move the local position a bit towards or away from the player. Then, once we round the vector2 to an int, we can send it to the update mesh function where the chunk is regenerated after editing the voxel and setting it to a specified block type in the function's variables. I add a bit more functionality by creating an inventory system, but I won't be going through that today because it's very case specific and a jumble of code. The world is looking very empty at the moment, so let's add some cacti in the desert biomes and a pumpkin in the woodlands biome as a start. To do this, we will loop through each column in the terrain, then we loop through all of the blocks going down. So we start at the very top of the column, and while our current voxel is still an air voxel, we keep moving down. Then when we hit the voxel that is not air, we create a change to that voxel in that position. Then we can create a loop going upwards this time to create a straight column of 3 to 5 blocks for a cactus in the desert biome. For the pumpkins, in the woodland biome, we just spawn 1 block. We can do something similar for trees. For oak trees, I simply check if the block below is a dirt block in a plains biome. Then we create 4 wooden blocks going upwards. Then at the top of the stump, I spawn a grid of cubes using a 3D group loop like so. It creates a regular upright rectangular prism, but to add some variability, I simply use a random float generator and check if the value is above 0.5. If so, then add the leaf cube, otherwise we don't spawn the leaf block. Also, when I say spawn, I mean to change the voxel array's data. For the forest trees, I do something similar where I create a loop going up but a bit higher for the stumps, 12 blocks to be exact. Then, using the for loop with an interval of 2, I spawn rings around the stump. If the distance of the block is less than 2 meters, then create a ring. I do this for 4 to 5 times with the rings of decreasing size and boom, forest trees. To add grass and flowers was quite simple. I create another loop after the terrain loop that can go through each column of the chunk. I find the surface block by using the same strategy I used for the cacti and the pumpkins and the trees. If the surface block voxel is a dot block, then I create 2 squares on top of the voxel. For the flowers I add 1 square, and the UV depending on which type of thing it is, grass or flower as requested. When creating the 2 squares, instead of adding them to the same mesh, I create a separate mesh. This is used to reduce the number of vertices on the terrain mesh. I also do this for the water, which I will talk about now. To add the water, when I create the voxel array, I set all of the voxels underneath a threshold to be -1. In the mesh loop, there is a check to see if the current voxel is solid, and if so, then create a mesh around it. The definition of a solid voxel is one with a block index of above 0. So if the block index is less than 0 or -1, I check if the voxel above the water voxel is an air voxel. If so, then create the top face. The other faces of the water do not need to be drawn, so that cuts out time on generation drastically. I also create a simple shader graph that wiggles the Y component of the vertices to give the world a nice effect. The player is based on this asset I found on the asset store with a couple changes. To add buoyancy, I basically say that if the place position is less than the water level, then set the place gravity to be -1, otherwise set it to be 1. This creates bounty buoyancy. This isn't the perfect model, but it's good enough for a 1-week project. Also, I changed the post-processing profile of the scene when the player is underneath the water for that nice underwater effect. The process for creating seagrass and kelp is quite similar to grass and flowers. When we do the grass loop, we check if the surface level block is underneath the water. If so, then we add the seagrass. For the columns of kelp, I check if we can spawn a seagrass on the surface voxel. Then, if a random number generator is greater than 0.5, then we change that grass to kelp. To create the column, I just keep adding grass going up until we reach around 5 to 2 blocks underneath the water surface, where I can tell the kelp to stop growing. Finally, we will talk about optimizations. I had optimizations in mind since the very start of the project so that the experimentation was streamlined, but the reason I kept this for the end is so I wouldn't confuse people with the complex job system code. And limitations. If you have experimented with the job system, you will know that there are many limitations, such as not being able to use unity.random, arrays, lists, strings, and managed types, and other important things. Their output and input is always a native array, and there is no native list option easily available. Not to mention the limitations that the burst compile and iParallel job type have. With all of these limitations, the job system may seem bad, but the insane speed of multi-threading and the worker threads allows me to generate noise in 7 milliseconds instead of 2300. Just fantastic. The GitHub code has commented script, but due to time frames, I didn't worry that much about the cleanliness of the code. The GitHub is revised and updates, so a couple things may be simplified or changed, but the main idea is still there. So most of the multi-threading code is there, and if you want to look at it, then go ahead. So that concludes this week's work. If you've made it this far, I'd like to thank you from the bottom of my heart. I've been slacking for the last month or so because of school, but I'm back on the grind, and this next video is going to be my dream project with procedural islands and a fantasy England theme. So if you would like to see that, then you should definitely subscribe and try to get me to 1,000 subscribers by the end of the year. If you would like to see me continue this series, then please leave a comment, and if you're still here, here's a treat. If you go to itch.io, there's a playable version of this project on the link on screen. So you don't need to clone my GitHub and do all that boring stuff like download it and unzip it and all that. So with that, I thank you again for watching my video and say goodbye. Until